Hello friends, welcome to my channel. I am Dr. Sunil Kumar M. Hasmani, Associate Professor of Mathematics at Rani Chennamma University, Belagavi. So today I am going to discuss independent domination number in graphs. So in my previous lectures, videos, you can observe that I have discussed on dominating set, domination number and some related theorems. So today I am going to extend that parameter, that is independent domination number. So for my video lectures, I have selected this book called Theory of Domination in Graphs by Professor V.R. Kohli. He is a retired professor of mathematics from Gulbarga University, Karnataka. Presently, he is working on topological indices and related parameters. So I am referring this book for my next video lectures. So according to this, after domination number, they have considered independent dominating sets. Okay. So today we are going to discuss what is independent dominating set and independent domination number. Okay. So let us start with first we shall discuss what is independent set. Independent set, and second one is induced subgraph. Okay. So we need to know what is independent set and induced subgraph to understand the independent domination number. So let us start with independent set. Okay. For example, consider graph G on 5 vertices. Say V1, V2, V3, V4 and V5 are the vertices here. Say V1, V2, V3, V4 and V5. You can observe that V1 and V2 are adjacent, V2, V4 are adjacent, and V2, V3 are adjacent, V3 and V4 are adjacent, and V3, V5 are adjacent. Okay. Suppose there exists an edge between any pair of vertices, then we can say that those two vertices are adjacent. Suppose there is no edge, they are non-adjacent vertices. Okay. You can observe that this vertex V1 is not adjacent with V3, V4 and V5. Okay. So similarly V2 is not adjacent with V5. So next V3 is not adjacent with V1 only vertex, and V4 is not adjacent with V5 and V1. So similarly V5 is not adjacent with V1, V2 and V4. Okay. Therefore we can say that any pair of non-adjacent vertices are, they are independent vertices. Okay. So maximum cardinality, you can say that for this graph V1, say V1, V4 and V5. Okay. So consider set S. So V1, V4 and V5, they are mutually non-adjacent vertices. Okay. Then we can say that S is an independent set. Independent set. Okay. Called as S1. So consider S2. Say V1, V4. This is also independent set because they are non-adjacent vertices. So next S3. V1, V3. They are also non-adjacent vertices. So next S4. V2 and V5. This is also non-adjacent. This is also independent set. Okay. So among all independent sets, we can observe that S is the independent set of maximum cardinality. Okay. S is of maximum cardinality, and remaining vertices are of cardinality 2. Okay. So this is about independent set. So next one is induced subgraph. So basically in subgraphs there are two types. First one is spanning subgraph. Second one is induced subgraph. So here spanning means suppose if we say that H is a subgraph of G, then we say that H is spanning subgraph of G if vertex set of G is equal to vertex set of H. This is the only condition. Means number of vertices in H must be equal to number of vertices in G. Such a subgraph is called a spanning subgraph. You can observe that a graph itself a spanning subgraph. Okay. So induced subgraph means here we can take any subset of a vertex set G. Based on this subset, we can able to draw a graph. Such a graph is called an induced subgraph, or we can say that a subgraph which is induced by the set S. Okay. So consider one example here. So consider a graph on 6 vertices. Say V1, V2, V3, V4, V5, and V6. So first I can consider the edge as these three components, and I will label it as V1, V2, V4, V5, and V3, V6. You can see that this edge containing all 6 vertices. Therefore, H is a spanning subgraph. H is a spanning subgraph. So next, I am considering a subset of a vertex set, say V1, V2, and V3. Okay. So there will be 3 vertices here: V1, V2, and V3. V1, V2, and V3. So you can observe that V1 and V2 they are adjacent in G, therefore they exist an edge. V1 and V3 non-adjacent, therefore they will remain non-adjacent here. And V2, V3 they are adjacent. Okay. Then we can say that this subgraph is induced by the set S. Okay. So this is about induced subgraph. So next, independent dominating set. Independent dominating set. So just recall the definition of a dominating set. So graphically, suppose this is a vertex set. Okay. Any subset, so D is said to be dominating set. Dominating set. And this part is V minus D. A subset is dominating set means every vertex in say its complement is adjacent to at least one vertex in D. Such a set is called dominating set. So here, if you say that a dominating set D is said to be independent dominating set, if a dominating set D is said to be an independent dominating set, if I consider the subgraph induced by D must contains no edges. No edges means contains all independent vertices. Independent vertices. Okay. Such a dominating set is called independent dominating set. You can observe D is basically a dominating set with this extra condition. The condition is that the subgraph induced by the set D contains no edges, or every vertex in D must be an independent vertex. Such a dominating set is called an independent dominating set. So consider one example here. Consider a graph on 5 vertices, say V1, V2, V3, V4, and V5. So here, let me consider first a dominating set here. Say I will consider V1, V4, and V5. V1, V4, and V5. Okay. If I draw, basically it's a dominating set because you can observe that V minus D is what? V2 and V3. You can see that every vertex in V minus D is adjacent to at least one of the vertex in D. Therefore, D is a dominating set. Next, verify that whether D contains all independent vertices. Of course, because you can see that here V1, V4, and V5 all are independent vertices. There is no edge between any pair of vertices here. Therefore, D is an independent dominating set. Okay. So next, consider one more independent dominating set. Sorry. So here called as D1. So next D2. D2 is consider V2 and V4. Okay. V2 and V4 is a independent dominating set because you can observe that V2 and V4, V2 and V4, they are non-adjacent. Also, it is a dominating set because every vertex in V minus D, every vertex in V minus D, say v1, v3 and v5 are adjacent to at least one of the vertex in D. Therefore D2 is a dominating set as well as independent dominating set. Okay, so this is definition of independent dominating set. Next, independent domination number. Independent domination number. So independent, just like in domination number, is the minimum cardinality. It is minimum cardinality among minimum cardinality every among all minimal dominating sets. Okay, so this is domination number. So similarly, independent domination number means it's a minimum cardinality among all independent minimal dominating sets. Independent minimal dominating set. So minimal dominating set means there is no suppose we say that D is a minimal dominating set, means there is no proper subset D dash of D which is a dominating set. Okay, so same thing here. If I say that this one is D is minimal independent dominating set, minimal independent dominating set, if there is no proper subset D dash of D which is a minimal independent dominating set. Okay, so here you can see that for this graph D1 is also independent dominating set which is minimal, and D2 is also minimal independent dominating set. Also you can see that V3 V5 is also V3 V5, this is also minimal independent dominating sets. Okay, so here among these three minimal independent dominating sets, D2 and say D3 are of minimum cardinality. Therefore minimal domination, sorry, independent domination number of that graph is 3. It is denoted by I of G is, sorry, I of D is 2 here, sorry. So minimum independent dominating set of cardinality is 2, therefore its independent domination number is 2, and maximum independent dominating set is of cardinality 3 here. Okay, so this is about independent domination number of graph. Okay, now if we consider some standard class of graphs, okay, for example if I consider a complete graph Kn, so n greater than equal to 1, then you can see that in complete graph every pair of vertices are adjacent, there is no independent vertices, therefore I can say that independent domination number of complete graph is 1 here. Okay, so next, second one, if I consider a complete bipartite graph, 2 is less than equal to r and less than equal to s here, then independent domination number of complete bipartite graph is, so yes here. Okay, because s is the maximum and every pair of vertices are non-adjacent here. Sorry, not s, it is r here. R is minimum here. Okay, next, so similarly for star graph independent domination number is 1. Also for wheel graph independent domination number of wheel graph is 1. So next, for path graph independent domination number of Pn, I think it is again ceiling function n by 3. Okay, and for I think for cycle graph also it is ceiling function n by 3 here. Okay, let us verify for odd cycle. I think I have some doubt on independent domination number of cycle graph here. Okay, it is 2. Yes, it is correct. So independent domination number of cycle graph is ceiling function n by 3. So you can observe that independent domination number of a complete graph is 1, complete bipartite graph is r, star graph is 1, wheel graph is also 1, and cycle and path graph are same, that is ceiling function n by 3. Okay, thank you for watching. So next video we shall discuss some more new domination parameters. Thank you.